broad subject. It's rapidly developing. A lot of new insights are appearing. People are starting to agree in the field what the important things are. Sorry. So I hope that I can give you a general view on this and that I give you the keys that will allow you to understand where we are at when it comes to jet substructure in heavy ion collisions. So, okay, right. So QCD matter. At low temperatures, we have hadron gas where color is confined, hadrons rescatter. Very high temperatures, we know that a new phase of matter has to appear, which is the quark-gluon plasma, which filled the universe at the beginning, right after the Big Bang. Color is liberated, and at very high temperatures, it has to behave like a gas of quarks and gluons, given the running of the coupling, symptotic freedom in QCD. But close to the phase transition, around this 170 MeV or so, we wonder which are the properties of the plasma. We know through the equation of state, these lattice computations on super expensive computers, we've seen that there's a rapid crossover transition as you increase the temperature, and there's a large number of degrees of freedom that get liberated around this transition. So this signals that there's clearly something happening, and we can see that as you go to higher temperatures, you tend to approach the non-interacting limit, which might lead someone to think that this might be a weakly coupled system. This is the Stefan Boltzmann limit of non-interacting system. But it turns out that if you compute these quantities in holography at infinite coupling, you see that actually even at infinite coupling, these values would be around 3/4 of the non-interacting limit. So it turns out to be that these thermodynamic quantities are poor indicators of the nature of the plasma. So very high temperatures, very high energies, we get a nice separation of scales in which the interparticle spacing is much smaller than the interaction range, because here G is very small at high temperatures, and it's much smaller than the mean free path. In this way, perturbative QCD can be safely applied. However, it's true that resummation techniques can bring the validity of the perturbative methods to much lower temperatures, such as HDL and other methods that you might have heard of. However, really close to the transition at relatively low temperatures of 0.2 GeV, we wonder if it's a gas of quarks and gluons. These temperatures, alpha S is around 0.3, which means that G is 2. It's not so small. Therefore, these scales are now comparable, which puts into question whether we have long-lived excitations in this plasma. These quasi-particles might be absent given this lack of separation of scales. Quasi-particles need that the lifetime of the quasi-particle to be much greater than the mean free path, for instance, otherwise you don't have a well-defined entity. So we want to know is the degrees of freedom, its behavior at these temperatures that we access in our accelerators. So it turns out, as we've measured and simulated, that the this QGP, this system that we are creating for these collisions, is a very good fluid. It's its most remarkable property. There are very strong collective effects. There are thousands of particles that appear to be correlated according to the collision geometry, and they are well described by aerodynamic explosions, like little droplets of QGP that expand against the vacuum, like a small fireballs. Indeed, these numerical simulations of hydrodynamics work because we assume that what's happening in the collision is that the spatial anisotropies translates into momentum anisotropies driven by strong interactions between the components of this system. You can even see in some events that there's definitely a shape to them. wherever there is more energy, it's because the explosion was more violent, and it is across the largest gradients. For instance, in this case, you see larger gradients are across the x-axis. So this is a completely classical, so to say, behavior of hydrodynamics, and it was very surprising. People have extracted the values of the shear viscosity of this system by performing simulations, and it turns out to be really, really small. It's the smallest value ever found for any substance ever, and it challenges the weakly coupled description of the plasma, because as if you do such a computation in, let's say, you take n equal 4 superior mils at weak coupling, you will see that this ratio eta over S, shear viscosity over entropy density, it blows up, and it is natural to expect that at weak coupling. However, at infinite coupling, there's the very famous result of 1 over 4 pi, which is remarkably close to the value extracted in experiments. Very interesting. So you see these anisotropies are quantified through the flow coefficients, which correspond to this expansion of the spectrum of particles with respect to the event plane, this phi r. In experiments, they've measured these coefficients, which these preferred directions of particles, and as a function of the collision geometry, whether it's really overlapping or not overlapping, as a function of the impact parameter, so to say. And what they've seen is that there are very strong effects that are mass dependent, depend on the particle mass. This is also this is expected from hydrodynamic behavior, because once the fluid becomes particles, the particles with a greater mass, they acquire less momentum. So you can also see that there are differences between protons and between baryons and mesons. Baryons have 3 quarks, so they get an extra push from the medium. These are all well-established phenomena that are still resilient up to date, that are really signatures of the hydrodynamic behavior of the plasma. Hydrodynamic simulations can very well reproduce this behavior. There's the elliptic coefficient V2, which responds to these kind of deformations in the geometry, the V3 that corresponds to these triangular deformations in the geometry, and higher order coefficients, and so on. So I won't talk about the flow in small systems. It's a very interesting topic as well, but it is clear that in heavy ion collisions in large systems, we really have a system that is evolving hydrodynamically with very low viscosity. So how can we probe this QGP? We cannot perform a fixed target experiment on it. What we have are jets. So take one parton from each of the, let's assume these are 2 protons, let's assume a proton-proton collision. 2 partons that participate in a hard scattering produce 2 back-to-back partons, back-to-back in the transverse plane, but not necessarily, of course, not back-to-back in rapidity, because the center of mass of this partonic collision is not the lab frame, right? We don't know which the longitudinal momentum of the incoming partons are. This will be important later on. These jets, these initial hard partons, they will start to radiate. They will relax their virtuality through successive splittings. Collinear and soft divergences make these objects collimated. Also color coherence that contributes to angular ordering that I will talk later on. Then we define an algorithm and a reconstruction radius, and we get our jets, which are proxies for the energy and properties of the initial hard parton that initiated the shower. So this is how jets in PP look like. Pretty clean, pretty obvious where the 2 objects are. However, in heavy ion collisions, there's a large fluctuating background that represents an enormous challenge for every kind of jet measurement that you want to do, because you need to subtract the background in order to know what the actual energy of the jet is. definitely one of the greatest challenges in jet physics is background subtraction. So let's start with a clear example where you will see the role of substructure into understanding traditional observables. When I mean traditional, I mean some of the first, for instance, dijet asymmetry. You can see here in this histo that you have one big jet of 200 GeV and another subleading one of 70. This is a heavy ion collision, and this is a very clear example of dijet asymmetry. One of the jets has lost more energy than the other one. This, in vacuum, there's also a natural asymmetry, but this value, this precise combination of 270 is very likely that it has suffered energy loss. In any case, the traditional assumption was that one of the partons was created at the, let's say, at the periphery, so that one of the jets went outside of the fireball without being touched, and the other one went through more length. Basically, a path length difference within the QGP. That's very clear and intuitive. And it's based on the single parton energy loss processes logic. But this was developed in the late 90s, early 2000s, and there are a set of processes that I will not discuss, which are medium-induced radiation and elastic collisions that, as you can imagine, contribute to the degradation of energy of the high energy particle that crosses this medium. And all you need to know is that they are controlled by the transport parameter Q hat, which is the amount of transverse momentum squared per unit length acquired through the medium. This Q hat parameter really contains a lot of the information about the interaction between the jet and the medium. So one of the very well-known models in the market, which is Joule. It's an energy loss Monte Carlo model. Essentially, the partons will collide with the medium scatterers, and they will get new kinematics due to these collisions. Then these new kinematics could potentially lead to a different splitting process, a different radiation pattern. Then, in order to decide whether this new radiation pattern is assumed or not by the actual shower, you do a check on the formation times. You check which formation time is short. This naturally includes the LPM interference effect, which is an interesting effect. It's a destructive interference in which radiations that are not yet well formed can get corrected or distracted by collisions through the medium, and the Joule does exactly that. So this is a very well studied model, and as you can see, it describes dijet asymmetry pretty well based on this quantity, AJ. It's the difference in the PTs of the two jets. So an AJ of 0 means no asymmetry at all. Here in blue, it is the PP result. As I told you, there's a lot of asymmetry also. But once you go to let this asymmetry is greatly increased, and Joule correctly describes it. So let's look under the hood of the Monte Carlo model. Let's put these two. Let's compute again the dijet asymmetry, but set the two jets at the center so that you make sure that they are traveling the same medium, the same amount of length. And what you see is that there is no difference if you compare it against the full result, in which the creation point is scattered across all the overlapping surface of the two nuclei. So how can this be? How can it be that dijet asymmetry has nothing to do, or is barely anything to do, with the amount of length traversed by each of the jets? Well, solution is in jet substructure. What they observed in this paper by Millano and Zapp is that the amount of energy loss as a function of the energy of the jet is delta PT over PT. It really depends on the mass over PT ratio. So how massive that jet is compared to its energy. The mass of the splitting, so the virtuality of the splitting, of the initial. this is done for a variety of jet energies, and it's quite clear that all of them follow the same trend. So why is this? Well, a jet, even though it can have, two jets can have the same energy, and they might be within the same jet radius R, that doesn't make them into equivalent jets at all. They can have a different fragmentation pattern. These two jets in this picture, they have the same energy and they have been reconstructed with the same cone. However, their fragmentation pattern is very different. Wider jets, they have more energy loss sources. Each of these partons is contributing into radiating energy out of the cone. So there's more quenching, there's more energy loss for these kind of patterns than for the narrower ones. Here, of course, we are assuming that most of the energy goes outside of the cone. This is something that we will need to address later on by talking about medium response. And also we're assuming that the internal structure of the jet is resolved by the QGP. You might ask, how separated do two color charges need to be in the plasma to behave as independent objects that radiate or lose energy in the plasma? If they are arbitrarily close by what is allowed by a parton shower's regularization, they cannot be arbitrarily close in angle. That would be non-perturbative regime. But how close, how separated do they need to be resolved? Otherwise, the medium wouldn't know which of them is wide, which of them is narrow. There needs to be some measure of that. That's also a relevant question that we will address.
Daniel, I'm a little, can I ask a quick question? So what determines whether it's a wide jet or a narrow jet? Is some initial optionalness or is it something else?
It's essentially, it's random. I mean, it's a parton shower is generated by the Diglap evolution, and this can be reformulated in terms of this stochastic picture that uses the Sudokuf distribution. The Sudokuf distribution is the probability of not radiating up from one scale to a given scale. So you have this probability distribution for radiating. So sometimes you radiate, so in some jets, if you start with the same maximum possible virtuality, which is the PT square, the energy of the object square, that's the maximum virtuality. And the minimum, it's something like lambda QCD square. You can, the first splitting can be in any place in between these two. So if the first splitting to enter the jet is of a high scale, then that will most likely behave like a wide jet. It can also happen, because it's a stochastic process, that the jet will have a low scale. The first splitting is a low scale. Then the next splittings will also be will have to be below this scale, because there's an evolution variable in which the splittings are ordered. It can be angular ordered, and so on. But I will focus on this later on. It will be important. Thanks for the question. Essentially, it's random fluctuations. So since we said that the medium is strongly coupled, I want to make a small detour and introduce some elements of holography that we will use for the rest of the talk. So there is this holographic dictionary that allows us to compute strongly things in strongly coupled theory by using semi-classical string theory in this ADS5 space. And the quarks are dual to open strings that are attached to the flavor grains. This is the, so to say, the real world dimensions at the boundary. This is the holographic direction. If you have a plasma in the gauge theory, that's equivalent to a black hole in the bulk. Then also the bulk metric perturbations, they encode the variations of the stress energy tensor at the boundary. This is how the dictionary sets up things, and it's a very natural field operator correspondent. Of course, most of these computations are done at n=4 subperiod mills, which is the simplest case or the most symmetrical one. And they have a very different vacuum. This theory has a very different vacuum than QCD, but at the finite temperature n=4 and QCD above the pseudocritical temperature, they share similarities. It's of course never an apples to apples comparison, these computations, but we do gain a lot of insight by computing these things in the infinite couple regime through holography. So there have been studies, several studies of jet energy loss in the context of holography, and one of the most
Daniel, your sound
has been the one that,
sorry, your sound got off. Actually, one thing we can try is maybe if you turn off your video, then maybe there's a bandwidth issue.
yeah. My internet is not great right now. I apologize.
No, yeah. Let's try it with this for now.
Okay. So what one can do is one sets this open string, starts at the boundary. All of its energy, most of its energy is along the boundary. Then what happens? You let this evolve. The black hole is going to pull the endpoint of the string downwards. As it goes downwards, parts of the string will fall into the black hole. That's energy loss. As the endpoint of the string gets pulled downwards, it also gets, the jet at the boundary gets wider, because the more deep you are in the holographic direction, the wider you are at the boundary once you project the energy momentum tensor at the boundary. So what's happening is that as the jet is losing energy, and most of the energy will be lost towards the end, because most of the energy of the string lies at the endpoint, and the endpoint is the last part of the string to fall. It gets wider. So this observation led the authors to state that this fractional energy loss will only depend on the initial jet opening angle. They computed an energy loss rate in this framework, and it exactly corresponds to the amount of energy that flows into hydrodynamic modes. So that's a well-defined quantity, and by using the null falling strings, they can have an unambiguous determination of the boundary jet properties. So it's a reformulation of the problem in terms of geometry, which is a lot of fun. It's very elegant, and it allows us to go to the strongly coupled regime. So Krishna and collaborators had this nice work, which is very convenient to the topic of this talk, in which they took an approach towards this jet consequent strong coupling, which is to consider that the string is a model for the jet as a whole. Okay, so if you take an ensemble of such jets, of such strings, and you let them go through this black hole that evolves in time, and you can arrange the initial properties of the jets, of this ensemble of jets, in such a way that they match to perturbative QCD. So such that the spectrum is a power law spectrum, such as we know, such as the angle, such as the variety of widths to some degree is representative of the variety of widths measured in some sense with respect to QCD. Because of course, all this cannot be done in holography. So that's how things are matched. The initial production is Harton perturbative, and then they have an evolution which is purely strongly coupled. So what do they see? They see that, as we said, each individual jet widens, right? Each individual jet widens. However, given that wider jets lose more energy, the final effect turns out to be that you have a narrowing of the final distribution. You have a steeply falling spectrum, which means that it's much more likely to get, if you, let's say that you put a jet cut of 100 GeV, it's much more likely that you have a jet produced at 110 GeV that loses little energy, that's more likely to pass the cut, than not having a jet of 150 GeV that loses a lot of energy. Because production decreases with PT. So what you have is a selection bias towards those kind of jets that lost the least energy. This is what they see by computing the jet shapes, let over PP. This is the transverse energy distribution versus the radial distance with respect to the jet axis for 0.3 jets, radius of 0.3. And indeed, they see this narrowing. You see more of the energy of the jet is concentrated at the...
Daniel, just one sec. Your noise, your sound just got reduced significantly.
Maybe I'm too loud.
Yeah, this is it.
Sorry. Yeah, okay. So it's, in this case, we saw that wider jets lose more energy because they have more energy loss sources, right? In this case, wider jets lose more energy. Why? It's because in this falling string setup, the initial width of the jet is determined by the angle it has, by the inclination it has in the holographic direction. So a very narrow jet, it has a very small angle. The direction of the endpoint of the string is very parallel to the boundary. But the wide jet, it's kind of pointing towards the black hole. The more wide it is, the more a higher inclination it has. So a wider jet naturally travels faster towards the horizon of the black hole. So it's a cool analogy, and it's interesting that these guys managed to get this feature, which is a key feature of all jet substructure observables, by using this holographic setup. So even in holography, what we see is this selection bias. What we did is took a different approach in which we assume that actually the splittings of a jet are to be considered perturbative through the Diglap evolution. But however, given that the interaction with the QGP is strongly coupled, we will have a holographic description. Then we also have the energy and momentum that is deposited in the QGP. We assume that it hydrodynamizes quickly, and we treat it such that we conserve energy and momentum. So in this model, which is called the hybrid strong weak coupling model, because we have this hybrid duality evolution, which is generated through Pythia 8. Then we have we assign a formation time argument for the space-time picture, so that we can assign space-time picture to a momentum shower, such as Pythia 8. Then we will use this expression from holography such that each of the partons that traverse the plasma will lose a certain amount of energy according to this rate that has features this stopping length, which is the maximum length it can traverse, and it has this order 1 free parameter. So we will also compute the modified hadron spectrum that comes from a perturbed freeze-out hypersurface. So the energy and momentum that the jets are depositing in the plasma, it will of course contribute into the jet observables because they are correlated with the jet direction. Even if you subtract the background, you will still have a signal coming from this. We will have a look into it later on. So let's start our journey into understanding the role of jet substructure by looking at classical observables such as jet suppression and hadron suppression. So if you're not familiar with the name RAA, basically computes, it's a ratio of spectrums between let and PP, normalized to the number of collisions that you expect. So seeing that you have a ratio smaller than 1 means that you have a suppression. So there's a shift in the spectrum because these objects are losing energy. So how do we understand the high momentum behavior, which is the regime in which jet quenching applies? This soft part is more completely dominated by hydro. And why do we have a different asymptotic trend for jets than for hadrons? So first, let's look at the jet substructure such as the jet fragmentation functions. They basically count the number of hadrons per jet with an energy fraction Z, right? So if you only have one jet, one parton in a jet, one hadron in a jet, sorry, Z fraction is 1, there's only one of them, okay? If you have a distribution of them, you have a distribution in Z, you take the ratio between let and PP, and you see that there's an enhancement in the high Z, which means, first, sorry, let me just comment that there's an enhancement in the soft part, which means there's an extra number of soft particles. They have been described through medium response or also the decoherence of the antenna. I will not focus on this right now. We're focusing on the hard part. Atlas more clearly sees an enhancement of hard fragments inside the jet fragmentation functions. So given that there's a steeply falling jet spectrum, it's very likely that the hadron spectrum at high PT, the hadron spectrum itself, is dominated by the leading tracks from the hard fragmenting jets. Again, it's because of the steeply falling jet spectrum. It's more likely to get a high PT hadron from a jet that fragmented hard, which means low fragmentation, than getting it from a higher PT jet that fragmented widely. Okay. Indeed, if you look at the average Z fraction of these for the different hadrons in the spectrum, they correspond to a Z fraction which is pretty high. Of course, they are the leading tracks of the jets. So the high Z region of these jet fragmentation functions are closely related to the hadronic spectrum. So let's look at how these jet fragmentation functions relate to the hadron spectrum. Let's assume we have this calculation of jet RAJ, jet suppression, and hadron suppression from the hybrid model. So now if we make a convolution between the jet spectrum and the jet fragmentation functions properly binned, of course, what we get back is the hadron spectrum for let and PP, and in particular the ratio. This is a ratio spectrum, RAJ. Of course, this could only be this way. It's a tautology. All the hadrons belong to some jet. Then we can play and let's assume that the fragmentation functions are trivial. There is no modification with respect to the vacuum ones. Then what you would get is that you have a trivial shift of the shape in suppression. We no longer have less suppression for hadrons than for jets. We can even go crazier and just invert the jet fragmentation functions, and we would see that we would have more suppression for hadrons than for jets. This is actually not crazy in the sense that there are some models which have a lot of radiation. They have a lot of radiation, which, however, does not go to large angles, in which this can happen. So imagine if you have this parton that radiates a lot, but the radiation stays collinear, then it's still within the cone, so no jet energy loss. However, there is hadron energy loss because that fragment itself has lost a lot of energy. So it's very important to understand jet substructure and how jet substructure is quenched in the medium in order to understand apparently basic things such like total jet suppression compared to hadron suppression. So this is no longer anything surprising. This is once again this very basic fact that wider jets lose more energy than the narrower, hard fragmenting ones. In this high PT hadrons belong to the subsample of jets that are narrow, which get less quenched. You could think about the hadron spectrum as some kind of limit of a radius going to 0, right? So that's pretty clear. Jet fragmentation functions, hadron spectrum, and jet spectrum are of course not independent objects. We make an interesting connection between them, and you can understand that the high Z enhancement is a key part of our understanding of hadron suppression itself. But we wonder how well does the QGP resolve the internal structure of the jet, right? How well does the QGP tell us whether it's a wide or a narrow jet, which is its resolution power? So let's have a quick look into the physics of coherence in vacuum, just an heuristic interpretation. Let's imagine that you have a virtual photon that decays into a quark and an anti-quark. Now you wonder about which is the angle of emission for a further gluon radiation. One needs to think in terms of formation times. Formation time, it goes like this. Formation time of the gluon. You basically get to it by looking at which is the time at which the wavelength of the gluon can resolve its separation from the quark. And a similar logic applies to what we do now. The transverse size of the gluon, 1 over the wavelength. Size of this antenna when the gluon is being emitted is nothing else but the angle of the antenna times the time at which the gluon is formed. So now if we compare the two, imagine that the opening of the antenna is smaller than the gluon wavelength. Then the gluon cannot resolve the pair, so we are in the coherent regime. And given that in this case, this is a color singlet, because this is a photon, emission is forbidden. The only way in which emission would be allowed is, so the area which is forbidden is precisely angles that are above the opening angle of the antenna. Because for such angles, the gluon cannot resolve that there is actually individual color charges and only sees the total 0 color charge. If the size of the antenna is greater than the wavelength of the gluon, then this gluon can start resolving the individual charges. And in this case, and for that, it needs to radiate inside the angle of the antenna. This is, in essence, the origin of angular ordering that is introduced in parton showers. And what you need to know about the medium, which I won't go into detail, is that in the medium, the typical wavelength is determined by the interaction potential. It's a screened potential, it has an infrared regulator, which for a dilute medium would mean that the typical wavelength is simply the Debye mass of the medium, while for a dense medium, where you can accumulate a lot of more momentum for several collisions, it's proportional to Q hat times the time of travel inside the medium. Also important is that the color correlation can be lost through multiple scatterings. You imagine this antenna, it keeps getting kicks, so its color gets rotated such that the correlations between the two objects are lost, and therefore coherence is also lost. So what we did, let me check the time. Did we start at 1:30? Okay. So what we did within the hybrid model is to assume a picture in which the resolution length of the QGP, it can be described as the minimum distance between two color charges such that they engage with the plasma independently. In this way, the medium perceives the parton shower as a collection of effective probes. This, at weak coupling, there's a clear connection between resolution length and energy loss. However, in strong coupling, there is no such connection yet. And in the hybrid model, we argued by physics of screening that this resolution length should be proportional to the Debye length. We test two extreme cases. Imagine that you can resolve arbitrarily closed configurations. So the fully resolved case. And when the resolution length is infinity, which is the fully unresolved case. So this means that the medium is only seeing the initial parton, it's not seeing any of the splittings, no matter how wide. These are two extreme cases in which we want to study some of the observables and the response to those. Of course, total jet quenching depends on this aspect. So the fitting parameter needs to be adjusted to be able to compare apples to apples. So there's this new substructure methods that are called the grooming procedures. And one can use the so-called soft drop, in which you reconstruct the jet with NTKT, then you recluster the jet with Cambridge-Aachen, which is an angular order clustering algorithm, and you go back the clustering history and look at the energy fractions or the angular separation between this pair of branches. So people do this in order to gain access to perturbative aspects of the shower, because in a jet there's a lot of soft crap, soft hadrons that are just just that contamination to some of the physics you might be interested in. So by looking at these steps in the clustering shower and by imposing some condition on them, whether you reject them or study them, you are actually selecting different regions of the phase space of a jet. This is the soft drop condition. It's not particularly relevant, the specific form. The thing is that you can either study the first splitting or you can study all of the splittings. And then you can access things like the number of splittings that passed your condition. And these are proxies for the multiplicity that, for instance, have been studied for quark-congruent discrimination. So let's look what happens, how do these observables depend on the resolution power of the plasma. We first look at the number of soft drop splittings, and you can see that when the shower is resolved, there's a shift to the left with respect to the vacuum case. There's again a selection bias towards those jets that have the least splittings in a completely analogous way in which we described the explanations for the rest of observables before. However, if there is no resolution of the internal structure of the shower, there's barely any modification. Look also at the momentum sharing fraction, at the Z fraction of the first soft drop splitting to pass the shower. This has been widely studied in sequencing phenomenology with a lot of relevance. And recently, Elise managed to do it differentially in the angular separation between the two splittings, between the splitting. And what they saw, or well, first, let's say what we saw is that there is a strong ordering in this angular separation between the two branches if the parton shower is resolved. If it's not resolved, then of course the medium cannot tell which jet was wider than the other one, so the separation is less. Much less, and the origins of the separation are quark-gluon fraction and some small hadronization effect. So why is this happening? If we have a larger angular separation between the two subjects, we have a larger phase space for emissions, therefore larger quenching and smaller survival rate. So back to this picture, the scale of the emission, it can be PT, angle, mass, formation time. This variable is really connected to this angular separation of this first, to the angular separation of the splitting. The virtuality is proportional to the angular separation. So we were saying before, if it happens that the first emission inside the cone has a large angle, then we know that the scale was relatively high and that there is more room for further emissions before you reach lambda QCD. However, if that first splitting that we are accessing through soft drop has a small radius, has a small angle, then the scale was low and there was few phase space for further emissions. So we really, by looking at this groomed angle, at this angular separation between these two clustering steps, we are really accessing the jet activity. So that's why we get what we get only if the medium resolves the shower.
So still a little bit confused about that this diagram. I mean, are you assuming that both cases have the same virtuality, and then you're just taking two cases where one has a big first splitting and the second one does not. Is that the picture I should keep in mind?
Well, the virtuality is different between these two guys.
Okay. Right.
So the virtuality is determined by this random distribution, by the Sudokuf distribution.
Okay. Okay.
You know the maximum virtuality, but you don't know which the actual virtuality will be.
Okay.
And by looking at this angle, you gain access to that. So that's why this is such an important and clear effect of the selection bias. Yeah, let me just skip. Embedding into a realistic background is crucial. So many statements were made about the modification of the splitting function, but realistic effects were not taken into account. And a model such as ours that doesn't have a modification of the splitting function per se can reproduce the data if you embed it into a realistic background. So yeah, always compare to right. So we've seen that the selection bias plays a very big role in all of these observables. So you might wonder, how do jets that have been quenched actually look like? So far, we've been looking at the jets that didn't lose energy. Those are the ones that tell us, oh, there's been a narrowing. Yes, of course, because we're selecting the jets that pass the cut, that pass the, let's say, greater than 100 GeV cut. These are the narrow ones. The wide ones, they went away. Or the ones that lost more than a certain amount of energy, you don't see. So this is common to all calculations and jet Monte Carlos that include jet substructure fluctuations. So what we can do is use machine learning to try to extract jet by jet the amount of energy loss. We can, given that we can look at the final energy of the jet, of course, the one we measure, and we define the ratio by dividing this energy by the vacuum energy of the jet, which is the energy that the jet would have had if there had been no medium. So this is the true energy loss ratio. It can be defined in most models where the vacuum part of the evolution can be separated from the medium part of the evolution, which is most models nowadays because of the solid physical arguments. So we can take the jet image as inputs for the neural network. We can look at the jet images just to get an idea for jets that correspond to different classes in this energy loss ratio. These are the least quenched guys, and as you move through here, you get to the most quenched guys. In the most quenched, you see that they have this corona of soft particles, right, all around it. This is the basic thing we know about jet quenching, is that there's a degradation of the hard modes towards the soft modes, right? Energy is being redistributed from the high energy members of the parton shower to the soft particles, and some of them part of the medium itself. Here the image has been rotated such that the subleading branch, the one we use to define delta R precisely, is at -π12. We don't want the machine to learn these kind of symmetries of space-time, so you try to help it. And we use these as images, as inputs for a convolutional neural network, and we do get very good results. We can predict the energy loss ratio with a good accuracy across most of the ranges, from a lot of energy loss ratio of 0.3 to a little energy loss of 1. We check that the vacuum jets, indeed, they do get values of chi, this energy loss ratio, close to 1 after training on medium jets only. And what we saw, we did a lot of analysis on the interpretability, and it is the jet shape, which is the transverse energy distribution with respect to the jet axis. It has a lot of information, a lot of discriminating power about how much energy was lost by the jet. Then we can use this to get rid of that selection bias we were talking about. Imagine that you have this final energy selection setup, which means that you select jets according to the energy you measure. That's the only way we can do it so far, right? You measure a jet. If it's greater than 200 GeV, you put it in your histogram. Otherwise, you don't. Even if you classify jets according to quenched or unquenched class, let's say greater than 0.9, which means unquenched, or smaller than 0.9, which means more quenched, the differences are small. And it's because still most of the jets are unquenched. There's a very little fraction of jets that are very quenched. So the statistics is extremely poor. However, if you use your knowledge about the energy loss ratio to select jets according to their initial energy, which is nothing else but the energy you measure divided by the energy loss ratio, then you are actually getting the jets that belong to the quenched class. They really are very quenched. And here you see the actual effects of energy loss. This is what you get in experiments right now. You get a narrowing of RG. And therefore, and the only explanation for this is a selection bias. It's interesting, but still boring in the sense that it's common to all models. You're not really seeing what the effects of energy loss are. And here, in this case, you do actually see it. You see that there's been an increase in the ground radius at high values, and it is because of the medium response particles. Medium response particles, they are soft particles, but they can get clustered into a new branch that satisfies the cut and gets this huge push here. So we should release this paper pretty soon with a lot more info about it and also some tomographic applications. I think it's cool. So before I finish, let me comment on recent developments on the wake of the jet. So this is a figure from a very important paper in 2007, where Chesler and Yaffe, they computed the wake of the jet, which is the response of an hydrodynamic fluid to a perturbation. Actually, indeed, at strong coupling and at largency, the string acts as a perturbation. And what they observe is a very good agreement between hydrodynamics and the wake of this quark within holography. So distances, even of the order of 1 over the temperature, this wake already behaves hydrodynamically. So it's very, as it's natural at strong coupling, very fast hydrodynamization of energy and momentum. This is, of course, all this medium response business is extremely important solely from an energy momentum conservation point of view. The momentum has to be conserved. So in the hybrid model, we had these hadrons from the wake. We did an estimate of the hadronic spectrum that comes from perturbing the hypersurface. It's a simple formula, but it's fully constrained by energy momentum conservation, no free parameters, and it has the advantage of being very efficient. So it's really expensive to run hydrodynamic simulations for each jet. But this was good. And this already has some very nice features. Like, for instance, the distribution as a function of the angle, it can become negative, which means there's a depletion of particles in the direction opposite to the boost of the jet. It's precisely this cosine phi function here. So there is a depletion of particles in the medium in the direction opposite to the jet, which is completely natural because of the diffusion wake. So then one can look at which is the jet suppression as a function of the jet radius and study this contribution separately. If you don't include any medium response, you have more suppression for wide jets. Why? That's the whole motto of this topic. Wider jets lose more energy loss sources. However, if you include the contribution from the medium response, which means energy is not lost, it is somewhere, if you include only the positive contribution, right, what you see is that you start to recover the energy already, and you can get to values of RJ even close to 1. However, you do not get to 1 to fully recover the energy because you have nuclear PDF effects, which have been largely ignored, but they are not small. So an REJ of 0.8 at a 1 TeV doesn't mean quenching. It might simply mean nuclear PDF effect, which is the initial spectrum has been modified because of the nuclear parton distribution functions in lead nuclei. Then if you include all the contributions, also the negative, then some of these negative contributions get do hit the radius of the jet, and they do lead to suppression. So it's a very rich interplay between the two jets. Indeed, the wakes of the jet, they can affect each other. You always have a dijet system, right? There's always one jet that loses more energy than the other for any reason. And therefore, this guy will have a larger wake. And the larger wake of this guy, it can affect the other jet only if they are aligned in rapidity, because the distribution of particles from the wake in rapidity is pretty narrow. While the rapidity separation between the two jets, it can be, as we said before, the center of mass of the collision is not the lap frame, so they can be at any rapidity, especially at the LHC and at relatively high PT, not super high PT. So we can study dijet systems with different rapidity gaps. And we do this here. This is the wake from the subleading jet, and this is the wake from the leading jet. And if they are close in rapidity, the negative contributions hit each other. While if they are separated in rapidity, you see this negative dip that happens at pi from the subleading jet. This is the positive contribution of the subleading jet. This is the negative contribution of the subleading jet, which is not hitting the leading jet. Therefore, there is less energy loss. So we can study jet suppression as a function of dijet rapidity separation for different radius. And this could be a very clear signature of the hydrodynamization of energy in jet quenching. We have recently improved the wake description. We want to see which effects are we leaving out by our oversimplified treatment. We can put perturbations on top of a viscous Bjorken flow. Here you have an example of the evolution as a function of time for the energy perturbation with the sound modes. This is for the velocity perturbation with the diffusion modes. Then we can also include the effect of the background flow by boosting the fluid cells according to a hydro background. And we can compare how this improved picture of the wake works against the hybrid model formula that I showed you before. And what we see is that the most important effect is the background flow. And this means that the wake is actually riding the flow of the medium. So if the jet is relatively well aligned with the flow, with the background flow, you will get an important push of the spectrum towards larger values, a hardening of the spectrum, and even a negative dip, because there are no more soft particles anymore compared to the case in which there was no jet. Also, as expected from hydrodynamics, we expect to see mass ordering even in the hadrons that come from the jet, because they hydrodynamize. This is an obvious consequence if you assume that the QGP is a fluid system. Also, there's an increase in the number of fragments in the number of fragments at higher Z's inside the jet fragmentation functions, mostly because of the flow, and the energy recovery as a function of the angle also gets modified. You have this non-monotonic behavior because at some point you also hit the negative part, okay? So this is a recent paper. If you're interested, take a look. And these will be included in the hybrid model soon enough. And stay tuned. I'm sure many cool things will be observed. So finally, I know I'm a bit over time. Finally, I would like to kind of condense what we have learned is important throughout these studies, throughout this talk. What we have seen that the jet substructure fluctuations are very important for our understanding of a great deal of jet observables. And the jet Monte Carlos naturally include these effects because they just let the jet branch and then everything happens. You just quench the partons, and sometimes it's a black box. You don't actually know what was going on. Now we realize these jet substructure effects are very important. So it would be great to have an analytic understanding of this. So what we need to do is we need to resum quenching effects that come from the multi-prong nature of jets. So a jet is not just a single line, a single pattern that goes through the plasma, and then it has a radius, meaning if I radiate inside, it's not energy loss. If I radiate outside, it's energy loss. It's not that simple anymore. Jets are a collection of patterns that are propagating inside the plasma, and jets with different radius are different. We also need to take into account the color coherence effects. Only the emissions that are resolved actually contribute to energy loss. Also important is to gauge the uncertainties on the non-perturbative components, such as the wake, which can have important effects. And we need to embed it into a realistic heavy ion environment. Even though we want to have analytics, these analytics need to be respectful of the medium path fluctuations that the jet experiences from one event to another event. So this is just a very brief sketch of the ingredients that go into this computation. You have a cross section for jets with a radius r, and they are the convolution of this initial partonic spectrum that, through a fragmentation function, goes into a jet of a given radius. And this fragmentation function, actually it's a moment of the fragmentation function, and this is within the context of the generating functional framework from Dasgupta and friends, where they made a very major step into computation of logs for small radius. The key point is that this gets corrected by a quenching factor within this generating functional approach. This quenching factor is the solution of this nonlinear evolution equation. This is a resummation of a single quenching factor, the quenching factor of a single guy, resummed over the many legs of the jet. Here are the Rayleigh-Parisi splitting functions, and this is the phase space of the phase space on which the resummation takes place. This phase space is precisely the place where we include the effects of coherence. Only those emissions that are formed before they decohere and that are inside the medium will be quenched. The initial condition for this evolution equation is the quenching weight of a single guy that has a radiative component in Laplace space. It's multiplicative. It has a radiative component and an elastic component, and the radiative component we have computed it with at next to leading order in the improved opacity expansion, which is the most complete expression for the radiation spectrum that includes both the multiple soft scattering regime and the single hard scattering. And this is some preliminary results. The paper should come pretty soon. What you see is that we have an excellent description of the PT and the centrality evolution for compared to Atlas data for radius of 0.4. And here in this picture on the right, you see that the values of the bare quenching factors, which is the quenching factor of a single parton, and in the bands, you see the effect of the resummation when you include the effects of the multi-prong nature of the jets. So a radius of 0.2 jet starts with this bare quenching factor. It loses more energy than a radius 1 jet because it has a smaller radius. However, it's less, in general, it's less wide. So there is less evolution from the bare to the resummed. On the other side, a radius of 1, it's the one that tends to lose less energy per parton because it can recover the energy because it has a large radius of 1. However, it has a lot of phase space that needs to be resummed. And what you get is that at high PT, you get this surprising independence of jet suppression with the radius r, which is also in agreement with the recent CMS data. And here also some of the effects of the wake are not included, and they are important. So this is a purely perturbative calculation with with one parameter that controls how much energy are you supposed to recover with increasing angle. So this is my summary. We see that jet substructure fluctuations are key to understanding of phenomenology in jet quenching. The early fragmentation pattern of the jet is dominated by vacuum physics because the largest virtuality comes from the hard scattering itself. And the largest virtuality will lead to the earliest formation time. So the vacuum-like splittings are the ones that form the earliest. This is natural in every model. We've seen that there's a selection bias towards narrower jets due to the steeply falling spectrum. This is absolutely key to understand almost every jet observable. Of course, provided that the medium resolves the internal structure of the jet. So this study that we made completely resolved, completely unresolved. There are still some models that assume that the jet is just a single parton. And they definitely cannot describe many of the features in data. So we hope that with this discussion, we can move towards this more updated description of jets. We have used machine learning to select jets according to energy loss so that we can plot observables in terms of the initial energy, for example, and we get rid of the selection bias. I also discussed the randomization of jet energy. So this is a very rich subject. It's being developed right now. And what we're seeing is that the weight is really sensitive to the background flow, the orientation of the jet with respect to the flow. It displays mass ordering. It could also depend on centrality because flow depends on centrality. And I also showed you this long range correlation between the wake of one jet and the other, that they can affect each other as a function of the radius r. So these are all crucial elements of the fluid PGP paradigm that need to be determined in data, need to be found in data in order to really nail down our interpretation of the nature of the quark-gluon plasma. So well, thanks a lot for your attention, and sorry for being over time. Sorry. Thanks.
Thank you, Daniel. Okay, so are there any questions? Are there any questions? I have a few, but maybe if other people have a few questions, please go ahead.
I know it was pretty dense, and I didn't stop at any particular point to give a lot of explanations. But yeah, feel free to ask about anything that sounded like, wow, what was this? What was this? And I can maybe explain a bit better.
Yeah. Okay, it seems like there are no questions from the audience. Please go ahead if you have any questions. Meanwhile, I'll ask a couple of things. So one thing I missed was this, you said that you had a way to extract the initial energy of the jet by looking at, of course, the final PT of the jet and some substructure observable. I think that was around 60 to page 62 or something. Yeah.
Yeah.
61. Yeah. 62. Yeah. So, I mean, I couldn't quite understand this chi m. I mean, that's not an experimental observable, is it? Or is it related to some experimental observable?
This chi, it's an energy loss ratio. And the only thing that's measurable in experiments is the final energy.
Exactly, yeah.
So what we do is we use machine learning so that the neural network tells us for this jet, this was the initial energy.
Yeah, so exactly. So the question is, what is the input to the neural network? Is it the distribution of particles or what goes into that neural net training or learning? Yeah.
this image.
The image
But
scores.
this is an average image. So
I see.
the image, yes. So this is of course the average image. Each individual image, it has a few pixels on it.
So my question is, but this image was created using a particular model, right?
Yes.
This hybrid model will have a specific connection of the final PT of the jet with the initial PT. A different model will have a different connection of the final PT with the initial PT. Is this understanding correct?
So yes, and that's the most important point. The one you have raised is that the generalizability of these findings to other models. And so there are two hopes. One hope is that to the degree that a set of models can describe the data similarly, that they should display similar features, and the fact that and that the consequences of energy loss in the jet image for these different models will be similar because they describe the data in a similar way. That's the hope. And also another hope is that, a thing that makes the generalizability possible is that in most models you can actually define the initial energy, because you need to train the neural network, and you need to know the initial energy, right? That's the true label, and then you try to predict it. Given that jet branching is a stochastic process, it might be hard always to find how the jet would have looked like if there hadn't been no medium, because it's a random number, you know what I mean? Sometimes it will be wide, sometimes it will be narrow. But given that most models have this separation between the vacuum part and the medium part, then most models are able to define this quantity. So what one should do is take, train the neural network as it's trained now, and you test it on another model and see whether it succeeds. And this kind of test will have to be done. But yeah, this, to the best of my knowledge, this is the best. This is the first study of jet quenching with machine learning in this way. So we expect that many more things should be done, and generalizability is the most important one. Yes.
Oh, okay. I see now. Here. And another question was related to your, it's I think page 28. There was a figure that was a bit unclear. The 28, yeah. So actually this, in this figure, what is the red curve? Is it the prediction of this hybrid model, or is it something else?
Oh, yeah, sorry. This red curve is the solution, is the prediction of this model. It's not the hybrid model. It's I don't know how to call it. It's this model.
Okay, it's purely holographic, basically. It's a purely holographic model.
Exactly.
But I assume that in the hybrid model, this issue will be resolved, or you will get this.
Well, this here is this race here is mostly due to medium response, and in this model they didn't have medium response.
I see.
So not having medium response means that you are not fulfilling energy momentum conservation. You are putting energy, you're saying energy is lost, but it's actually being put in the hydro modes of the plasma. So you need to look where this excess of energy that you put into the plasma ends up. So that's why it's crucial. You cannot ignore energy momentum conservation. So in this case, given that most of the energy is hydrodynamized, I mean, all the energy that is lost, it's because it's hydrodynamized. It will likely be an important effect. But they didn't push this forward. They didn't include the medium response, but they could have done it. Maybe they do some point. This was Krishna, Vilke, and Andrei. Yeah, was very nice. Very nice model. that show the selection bias from holography. That's interesting.
Yeah.
Yeah.